Okay, in this part of the lecture, we will discuss how the voltage will be when the current, a sinusoidal current is passing through an RL circuit, resistance and inductance circuits. So let's consider a current I of t, which is passing through this series combination of R and L, and let's say this I of t is represented by I of t is equal to Im sine of omega t. So the total voltage, regarding the Kirchhoff's voltage law, is equal to the voltage across the resistance VR and the voltage across the inductance. So we can write this as Vt of t is equal to Vr of t plus VL of t. So Vr of t is equal to I of t into R, which is equal to Im R sine of omega t. What about VL? VL of t is equal to L di t by dt, which is equal to L, and the time derivative of this is omega times Im and cosine of omega t. Okay, so we have now the total voltage is equal to Im R sine of omega t and omega L Im cosine of omega t. Okay, so we have now this expression, and let's assume that this equation is represented by equation 1. Okay, let's consider the trigonometric identity. That let's say we have a sine of omega t plus phi is equal to a sine of omega t cosine of phi and a cosine of omega t sine of phi. Okay, so we have this expression, and let's assume that this is equation number 2. If we compare the two equations, okay, so we can easily infer that R times Im is equal to a cosine of phi and omega L Im is equal to a sine of phi. Okay, so as I told you in my previous lecture, that when you are dealing with inductor, the current will always lag the voltage, the applied voltage, and that lagging will be by 90 degree or pi by 2. But if you include a resistance in series with that inductor, then the lagging angle will be less than pi by 2 or 90 degree. So let's see how this will be. Okay, so from these two equations, we can write this as tangent phi, which is equal to sine phi by cosine phi, which is equal to omega L by R, because Im is cancelled with Im. Okay, and A is cancelled with this. So here we can write this as phi is equal to tangent inverse omega L by R. Okay. Also consider that. Okay, let me remove this. There is no need. Okay, these are important. So the amplitude A is equal to, just computing the square, a square cosine of square omega t, a square sine of square omega t, adding the two, so cosine square plus sine square is equal to 1. So we can leave this a and square root of this. So r square im square plus omega square l square and im square. So it is r square omega square l square, and taking im as out of this square root. Okay, so this is the value of a, this is the value of phi. So then you can easily substitute these values. Okay, so the cosine phi is equal to, from here, the cosine of phi is equal to RIM by A, where A is nothing but this thing. So IM is cancelled with this IM, so it will be equal to R by R square omega square and square root. Okay, so if you look at this substitution and these things, then it represents an angle between the R and this magnitude. And just recall the complex representation of a circuit. So a complex number is equal to, z is equal to x plus j times y. So here, if you just compute the amplitude, you will have x square plus y square square root. Just look at here and look at this value. So this is equal to r square plus omega square l square square root. Okay, so we can represent this in this form. So we can represent it as r plus j omega l. So we can say that if you include inductance with a resistance, then this will lead you to a complex impedance, and it is represented by this representation. Okay, so if this is the case and we agree with this representation, then that complex representation is like this. Z, and we have R and we have omega L. So we have R here, we have omega L here, and this is angle phi. Okay, so the Z is equal to R square plus omega square L square. So just to avoid confusion, use the normal notation. Okay, so now from here you can directly compute that tangent phi is equal to omega L by R. So the angle, the lagging angle, is less than pi by 2 where resistance and inductance are connected in series like this. So just writing in the form of this. Now, if this resistance is very, very small, okay, then omega L. Okay, so what will happen? This phi will approach pi by 2. Okay, and if this resistance is very, very large, then this phi will approach to 0, because if it is very, very large, then this will of course approaches to 0 degree. So it means that if the resistance is very, very small, then the inductance effect will be dominant, and the phase angle, or the angle between the voltage and current waveform, will approach to pi by 2. On the other hand, if the resistance is dominant and inductive effect is very, very small, then it will behave like a resistor circuit, and the phase angle between the voltage and current is